Bismillahirrahmanirrahim. Welcome back to my channel. I'm back with a video on software-defined radio and GnuRadio tutorial. I haven't been making any videos on it, but after a long time, I'm making a video on GnuRadio. This video actually is going to be consist of two different things. First is going to be amplitude modulation, another way of generating an amplitude modulated signal using GnuRadio. This is much simpler, easier way to actually generate amplitude modulation. Remember last video that I made, I'll leave a link on it, at the end of this video, where I was using a lot of different blocks and I was actually using those mathematical equations and I was just mapping them using available blocks in GnuRadio Companion. Now this video is going to be much simpler. So first half of the video is going to be amplitude modulation, and second half of the video is going to be all about stem plotting. Stem plot we normally use in MATLAB and things like that. How you can generate stem plots using GnuRadio Companion and things like that. So let's go ahead with the demo. Same thing as we've been doing it previously. In order for me to generate any modulation, you need a multiply block. So we have a multiply block like this. You need to have your carrier signal and you need to have your baseband signal or information signal or modulating signal or your intelligence signal. There are different names for it. We're going to just call it a baseband signal. So the first thing is my carrier signal that is given by a cosine signal. If I were to double click on the properties of this, this is what I would see. I have a carrier signal. This is being called by this GUI range block that is going from 0 to 16 kilohertz, and the default frequency is 1 kilohertz. Straightforward amplitude is just 1, nothing fancy going on here. Second thing that I have is actually my modulating signal. Modulating signal has an frequency from 40 all the way up to 200 hertz. That is being controlled by this GUI range slider, which I'm calling it baseband frequency. The second thing that I have that is being controlled is actually going to be your baseband amplitude. So this baseband amplitude is also being controlled by this block. If you were to look at it, that is going from 500 milli all the way in a step size of 10 milli. So next is going to be, and going all the way from 0 to 2. So 500 milli, step size of 10 is going to be 51, 510, 520, 530, and so on, and is going all the way up to 2 volts. Let's think of it in terms of voltages, 2 volts. So from 0 to 2. Now the next thing is a label called modulation depth. This modulation depth that I have is actually the default value is divided by baseband divided by 1 times 100. So basically I am multiplying it by 1, multiplying it by 100. So for example, if I have a baseband value of 500 milli, divided by 100 would give me 50. All right, so 500 divided by 100 would give me 5, so which is going to be 50. All right, let's say I have a next increment is 510, so it would give me 51. So 510 divided by 100 would give me 51, and so on and so forth. So this is how this value is going to be. This is in terms of milli. So you will have an increment of your modulation depth in terms of 51, 52, 53, 54, 55, and so on, and it will go up all the way up to 2. Next thing, nothing fancy. This is just a GUI hint. The way the different your sinks are there is just the layout. That's about it. The next thing which I found really interesting, which will help me reduce all the different blocks that I was using previously to generate amplitude modulation, is actually that carrier offset. So I'm using actually a carrier offset of 1. So if you were to look at my last video, the actual video, the equation of AM is actually 1 plus, you have your carrier signal, then you have your bracket, you have 1 plus M of t times your modulation index. So that 1 is actually that offset that we were using add constant block. But here I'm just using that offset block. Offset of 1. So it's actually basically shifting my modulating signal to 1. I'll show you that what I mean to say. Let me just quickly run this flow graph, and I'll show you this in a little bit. So here we go. So now when you look at it, so this is my, let me just turn off my modulated signal. So this is my carrier signal first, that is going from 0 to 1, is swinging back and forth. Then you have my baseband signal that is right here, that is as an offset of 1. So just to show that the signal is riding. Now modulation is taking place when I'm changing the amplitude of my modulating signal. So by changing the amplitude of modulating signal, you are changing basically the amplitude of your carrier signal. So now let me just look at my modulated signal. So modulated signal is in green. So the amplitude is continuously changing. All right. So as you can see, this is my baseband signal, and my amplitude is actually, my modulated amplitude is following that. So by just removing the amplitude, baseband amplitude, I am controlling the modulation index as well, as you can clearly see here, and it's going in an increment of 10 millisteps or 10 millivolts, and you would receive a modulation index of about 100. But in my previous video, I was actually using multiple blocks to do that. But in this, I can just use a single block by incorporating my modulation depth and baseband together, amplitude together. I can clearly see that this is the modulation. So if I were to turn off my carrier signal, you can see that this is my modulated signal that is at 100% modulation. Now, what happened when I do over modulation? If I go over 100%, as you can see that you will see a phase reversal right in the middle of it. Not much you will see here, but you will see definitely a phase reversal at this end of my modulation, a modulated signal. So when I take this, so I have my over 100% modulated signal, then I have my under modulated signal, which is, let's say, somewhere around 50, which is like half of it, and then I'll have my over modulated signal, where you can see that my signal is being reversed at this end of my modulated signal graph or a wave. So this is what it looks like, and so on. So this was another basic demo that I would like to give you, where you can actually look at your amplitude modulation in a different way. The next step that I want to show you is actually stem plotting. It's a very famous way to plot. It's actually basically give you your signals in a form of a stem. It's a very popular way you can visualize signal in MATLAB. So the best idea to actually generate these. So I have two types of signals. First, I'm looking at a real cosine signal that is going to a Qt GUI time sync. And the next signal is actually a complex signal, which consists of your I and Qs. I and Qs are your cosines and your sine signals. So we're going to look at them individually. But how do I actually generate these stem plots? Just simply go in here, go to Config tab, and then you choose it. So for example, I'm clicking here because in your real signal, you don't have IQ. You're just looking at only the real part of a signal. So all you need to do, just go to your line width, select the color and the style to be solid, and this to be circle. That's it. Or you can have a rectangular, you can have a diamond shape, whatever it is. But a stem plot is normally like a circle on a line, and you have a line that is going to your horizontal axis on your time sync graph. That's all. That's how you generate a stem plot. Same thing here in quadrature sampling. Go to config. In quadrature sampling, we have I and Qs, so that's why we have two different lines. So one I'm representing using blue with solid and circle. The next I'm using it red, solid, and circle. Let me just show you what I mean to say. Let me run this demo and it will make sense to you. Now, the next step you need to do, I'm just going to simply run this graph. Now, you see that? So you have a solid line and then you have a circle. So this one is actually your quadrature sampling, and this is your real signal sampling. So you can see this, you can easily sample it by increasing the frequency. Now, when this frequency goes above a certain Nyquist theorem, you can see that you're seeing very less samples, because now this is almost, I'm sampling at let me look at my sample. I'm sampling at about 32 kilohertz, and when I change this frequency, so first let's look at it at 500. So the next step is actually the number of points that I'm choosing. So the more points you will have, the more visualization of the more samples, the more stem plots, the stem you will see. Let me show you what I mean to say. Just give me a minute. So here we go. This is my graph. So I'm choosing 64 points in both of these. So if I were to count these points, starting from here all the way down to this, I will see 64 points. If I start counting this from here to here, these will be 32 points. And from here all the way up to here, you will see 32 points. 32 plus 32, you will have 64 points. You can change these points as well. Because I have chosen 64, but you can change this to, let's say, 256, I believe, or anything raised to 2 power. You will start seeing more of these points closer. So here we go. You start seeing more and more of these points. So this is like complex sampling. So you will have your I and Q's. So you have I, which is real, which is actually your sine wave. This is, here we go. So this is your sine, and then you have a cos signal that is right here. So this is your real and imaginary signals. Both of these are being sampled, and this is only your real signal that is being sampled. So because cosine, sine is at 0, and your cosine is at 1. When it's 0, it's actually 1, and so on. When it's 0, it's actually 1. So this is your cos, and this is your sine signal, and this is being represented in terms of colors, and this is what you're seeing, only the real part of the signal. So this is how you actually generate these stem plots in GnuRadio. If you have any questions, leave it in a comment section. Don't forget to like and subscribe to my channel, and thanks for watching.